Hello. In this video, we're going to look at an application. Suppose a small pond normally contains 12 units of dissolved oxygen in a fixed volume of water. Suppose also that at time t equals 0, a quantity of organic waste is introduced into the pond, with the oxygen concentration t weeks later given by f of t equals 12t squared minus 15t plus 12 all over t squared plus 1. As time goes on, what will be the ultimate concentration of oxygen? Will it return to 12 units? Okay, so really what we want to know here is what's happening as t gets really large. So to look at that, let's see what's happening here. Really what we want to know is what is the limit as t goes to infinity of 12t squared minus 15t plus 12 all over t squared plus 1. That's what we want to know. Now, let's talk about this. Infinity is just an idea. It's not really a number. It's part of the extended numbers, if you will, but it's not really part of the real numbers. So we need a way of dealing with this. Okay. To do that, we ask ourselves, what is the largest degree in the denominator? Well, the largest degree in the denominator is 2. So what we're going to do is we're going to say this is the same thing as the limit as t goes to infinity, and what we're going to do is we're going to divide every term that we see in here by t squared. So this will be 12t squared divided by t squared minus 15t divided by t squared, and then plus 12 divided by t squared. Then again, all over the denominator of t squared divided by t squared, and then plus 1 divided by, again, t squared. Now notice that I chose t squared because that's the highest degree of the denominator. Now let's see what happens when we simplify that. This gives us the limit as t goes to infinity of 12 minus 15 over t plus 12 over t squared all over 1 plus 1 over t squared. Now here's the thing. Notice that as t gets really large, these numbers become really small. Because 15 over 10 is 1.5, sure, but what is 15 over 100? It's 0.15. And the 15 over 1,000 is 0.015, and then 0.0015, and then 0.0000000000000015, and so on and so forth. So as t goes to infinity, this literally becomes 0. And the same thing is happening here. And the same thing is happening here. So this becomes 12 minus 0 plus 0 all over 1 plus 0. And then you just simplify that. That's going to give me 12. As time goes on, what will be the ultimate concentration of oxygen? The ultimate concentration will be 12 units of oxygen for every fixed volume of water. Will it return to 12 units? Yes, it will return to 12 units. Now it may take some time, and technically no, because this is just a limit. This is what we call the horizontal asymptote of this rational expression. So technically, no, it won't actually reach 12, but it'll be so close to 12 for all practical reasons, it'll be 12. In other words, if it's 11.99999999999999999, that's 12. Come on, let's be honest. So the answer is yes. Now, another way of seeing this is to look at the actual function itself in the calculator, and I do want to see what it looks like. So I will go ahead and see you there. Okay, welcome to the calculator. I'll clear anything that's in here. So go to y equals, and then let's type this in. alpha y equals enter, and then do 12, instead of t, we have to do x, so 12x squared minus 15x plus 12 in the denominator, x squared plus 1. Fantastic. And then just graph normally. If you want, do the zoom 6, and this is what you see. It's not actually what we want to see, though. So let's go to Window. We're going to start at t equals 0, so x equals 0, and we're going to go to t equals something. Let's say t equals 25. For the y minimum, we want it to be 0 because there's no such thing as a negative amount of oxygen concentration. And for the x maximum, notice that it begins at 12, so let's go to 15 so we can see the 12. And see what that looks like. Here we go. So what we have here is the algae is actually reducing the concentration down to this point, and then at some point here, it begins to go back up and up towards this way. Now notice that it's taking a long time for it to go back up towards this 12. So just so we can see the 12 here, let's do the 12 there. And let's, can we make that dash, or not? Yeah, can we make it, come on now. Dashed, okay, good deal. That's not dashed. Maybe that will be. There we go. So this is the horizontal asymptote here. Notice that it's not really getting close to the 12. It is kind of, but it's doing it slowly. Now, T is the number of weeks, and we've only gone to 25 weeks here. And this is like, after 1 week, it really shot down, and it goes back up, and it's taking 25 weeks to just get back to around 11. So if we extend our window here, instead of 25, let's make it 100. Notice that we're getting a lot closer to the original value there. So if we extend this to 1,000, yeah, it does start appearing that it's pretty much exactly what it was to begin with. So what is that? Probably after 30 or 40 or 50 weeks or something like that, then it's pretty much indistinguishable to what it was originally. But it takes a while for that to happen. So let's go back to the 100 so we can see that again. There we go. Yeah, so it takes a little while. Alrighty. Well, I believe that's it for this video. I'm going to go ahead and end it here, and I will see you in the next one. Have fun.